Okay, good afternoon. So we'll continue what we started in chapter 3, which is a general review of vectors. So we already covered the gradient. Gradient is always applied to a scalar, and it gives us a vector with the with coordinates along x and y and z. And then we also can look at the divergence of a vector. So now we have seen that the gradient is always applied to a scalar, but we also have the divergence that is applied to a vector field. Divergence of a vector field. So mostly the divergence, we use it in when we try to calculate the flux, for example, the flux of the electric field, the flux of the magnetic field, and the divergence of a vector E, let's say the electric field, is equal to the derivative or the partial derivative of the x component of the electric field plus the partial derivative of the y component plus the partial derivative of the z component. Now, remember, the electric field is a vector, a three-dimensional vector in general, that has three components along y, x, y, and z. Okay, and this is a scalar quantity. Remember the difference between the gradient of a scalar that gives you a vector and the divergence of a vector that gives you a scalar. So we also call it divergence of E, which is this, and the divergence can be positive, the outgoing flux can be zero, and can be negative also. Okay. So as I mentioned, the divergence is a differential vector. It always operates on vectors, and the result is a scalar. There is also one important thing: the divergence and the gradient, they do not have the same expressions in cylindrical and spherical coordinates. We will see it later. There is an important theorem that is called the divergence theorem. We will use it mostly later when we will talk about electrostatic and magnetostatic. The divergence theorem tells us that the volume integral over a volume, if I take the integral of a volume over a volume of the quantity divergence dV. So if I take a volume and I want to calculate the volume integral of this, the divergence of vector E, it is equal to the surface integral, or the integral of a closed surface that contains the volume that I'm trying to calculate, for which I'm trying to calculate the divergence. So E, and this we have seen this in physics 207 in Gauss law. So this is a divergence theorem. Okay. So the divergence theorem tells us that the volume integral of the divergence of vector E over a volume V can be calculated as the flux, okay, this is the flux of this quantity, the electric field, through the closed surface that contains volume V. Okay. Okay. For example, if we wanted to calculate, let's say, the divergence of an electric field inside a sphere, so what we would do, we just calculate the flux that goes through the surface of the flux of the electric field that goes outside out of the surface E. So an example, a difference between the electric field, the divergence of an electric field and the gradient of a scalar. So for example, if I have an electric field that has, let's say, 3x squared x plus 2zy plus x squared z, and I want to calculate the divergence of E. So the divergence of E is equal, of course, the derivative with respect to x, okay, plus the derivative with respect to y, plus the derivative with respect to z. Let's do it directly. So the derivative of the component along x, x component along x is 6x. Derivative along y is 0, because there is no, this component, the component ey, does not have any dependence on the y-axis, so this is 0. And then the component along z does have, so it's x squared. So the will be 6x plus x squared. Okay. So, and then we have also another important quantity that is a curl of a vector. The curl of a vector. So all of this we have seen in electromagnetism in physics 207, but now we will use them extensively. That's why we are covering them. So the curl of a vector describes its circulation. The curl of a vector describes actually its circulation, like a kind of rotation around a closed contour. Remember, when you have an electric current, okay, that is going, let's say it's flowing, and then we wanted to calculate the magnetic field created by this. So we had the magnetic field, right? So it gives us the curl. How do we calculate the magnetic field? So we, in fact, we calculated this quantity, and this quantity, yeah, so this quantity is given, it's the integral over a closed contour. It is the integral over the closed contour. And the curl operator, we will define a curl operator as follows. The curl of the magnetic field, it's a cross product. And now you know that the cross product, you just do x, y, z, okay, and then bx, by, bc, and then you do calculation on a circular calculation. But the most important thing is the Stokes theorem. So the Stokes theorem gives us a relationship between this one and this one. Okay, so the Stokes theorem, which is very important, that's why I mentioned electromagnetism. This is what we use to calculate the electric field, the magnetic field, sorry, in any line, in any point, a magnetic field created by an electric current that is flowing across a wire, for example, and we wanted to calculate the magnetic field at any current that has a distance, that is located at a distance r. So the Stokes theorem is the following. It converts the surface integral of the curl over a vector over an open surface into a line integral of the vector along the contour C that bounds the surface. So if I have, if I want to calculate the surface integral of this vector, okay, over a surface, all what I have to do is to calculate the line integral of b dl. So we will use it and give some demonstration later. So here it, okay, so it's the curl of a vector. So we need to have in mind this one, this Stokes theorem. I will give some exercises later. And the last one is the Laplacian operator. The Laplacian operator is when we have multiple combinations of operations on scalar and vectors. For example, if I take V is equal Vx, Vy, Vz, this is a scalar, okay? Is scalar. Now, scalar, I can use a gradient to calculate the rate of change of the scalar, okay? This will give me V over X plus V over Y plus V over Z. And here I have, let's say, X, Y, Z, right? Which I can easily write as, let's say, Vx, X plus Vy, Y plus Vz, Z, right? Now I can also calculate the divergence of delta V, the divergence delta of this vector, because now this is a vector. Okay, so I can calculate the divergence of this vector, and the divergence of this vector will be the ax with respect to x plus ay, sorry, not a, v, because I used v. Okay, so vx, no, no, v. Actually, I used v. Yeah, so this one. So vx plus vy with respect to y plus vz, well, the derivative would respect to z. Now I can replace, I know that vx is the derivative of v with respect to x, so which means the second derivative of v with respect to x squared plus the second derivative of v with respect to y squared plus the second derivative v with respect to z squared. And this is then, this one is called Laplacian operator. Laplacian is this plus the second derivative y squared plus the second derivative z squared. Okay. Okay, so now let's take this example. So an example. So if I get, let's say, a scalar that is V0 exponential minus 2r sine 3 phi. And I want to calculate, so this is a cylindrical form, and I want to calculate the gradient of this. The gradient of this. Again, let me mention something about the gradient. Yeah. So let's first, before doing this, let's give a remark here. So the gradient if you look at the cylindrical form, the gradient of any V is equal to over R plus 1 over R V with respect to phi, and then the derivative with respect to Z. Okay. So we can apply it directly here. So this will give me, we are talking about the gradient of a scalar that has to be a vector. So the derivative with respect to r, it's minus 2 v0 exponential minus 2r sine 3 phi, right? Minus 2 v0 exponential r, yes. And then, so this will be r. And then the derivative with respect to phi is 1 over r. And this will be 3 times, so it's times 3 v0 exponential minus 2r cosine phi. And there is no dependence on the the z-axis. Okay, so you have a dependence on r, dependence on phi, and this is the gradient of this vector. The gradient of this scalar, which is a vector. Another example now, if we go to, let's say, calculate, if I take a, another example, if I take a is equal, let's give a vector, and this vector has this component cosine phi r plus r sine phi plus 3z z. Well, it is clear that this is a vector that is represented in cylindrical coordinate. The question is calculate the divergence of this vector. So the divergence of this vector, again, so this is the gradient of a vector. Okay. Now we want to go for the divergence, an example on the divergence. Now, it is important to know that the divergence of a vector, let's call it the divergence of a vector, in Cartesian form is ax over x plus the derivative of the y component with respect to y, the derivative of the z component with respect to z. This is in Cartesian coordinate. But our work here, our problem here is in cylindrical coordinate. So the divergence of vector A in cylindrical coordinate is 1 over r, the derivative with respect to r of r, AR is the component along r, plus 1 over r, the derivative of the phi coordinate, sorry, or the phi component with respect to phi, plus the component along z. This is the formula or the expression of the divergence of a vector in cylindrical form or cylindrical coordinate. Okay, let's apply to this. Here it will give me 1 over r, the derivative of r. What is the component of this vector along r? Is this one, r cosine phi. So it will be r squared cosine phi plus 1 over r, the derivative with respect to phi of the phi component, which is r sine phi. Okay, plus the derivative with respect to z of the z component, which is 3z. Okay, then this is the derivative with respect to r of this is 2 times r, so 2 times r divided by r cosine phi plus the derivative with respect to phi here is r cosine phi divided by r, and then the derivative with respect to z is 3. So this will go, it gives me 2 cosine phi plus cosine phi plus 3, which will give me 3 cosine phi plus 3. Okay, so I will post some recommended problems today on this, just to summarize the difference between the gradient in cylindrical form, for example. A gradient of a scalar in cylindrical form is the derivative with respect to r plus 1 over r, the derivative with respect to phi plus the derivative with respect to z. The divergence of a vector, okay, the divergence of this is in cylindrical form, and the divergence of a vector is 1 over r, the derivative with respect to r of the r times the component ar, plus 1 over r, the derivative of the component of phi, and plus the derivative to z. This is in cylindrical. This is to show you that the gradient in cylindrical form is completely different of the divergence of a vector in cylindrical coordinates, and the same thing for the spherical coordinates. Okay, I will stop here. I will give some recommended problems for the quiz on Tuesday, on Wednesday, and we will continue. So we are done with chapter 3, and we will continue. We'll start chapter 4 next Monday. But I will give you some recommended problems on chapter 3. Thank you.